accepted. Challenge accepted. Reality is always challenge accepted. Challenge accepted. Challenge accepted. Reality is always challenge accepted.
All right, folks, time to zoom into security at Google scale. You've probably heard of YouTube, Google Drive, Google Clouds, Google... all of them rely on a single authorization system.
And no, it's not your mother checking if you ate your cucumber, it's Zanzibar. The globally distributed authorization system that keeps billions of requests consistent and secure.
Our next speaker has traveled here from the land of canals, cheese, and windmills, Amsterdam.
He is a lead developer advocate at Authzed and has spoken at over 100 international conferences from AWS reInvent to Web Summit.
When he's not debugging tricky systems, he's probably winning at pub quizzes or throwing frisbees like a world champion.
Please welcome Sohan Maheshwar!
Check. All right. That was the most hype introduction I've ever received, so thank you. All right, so as they mentioned, my name is Sohan. I've worked in the industry for 16 years now, which makes me an old fart, as they say. But I'm so excited to talk to you about authorization and about specifically how Google built their authorization system and how you can too. I have a question to ask you all. It looks like a very young audience, so you may not remember this, but the slightly older people in the audience like me might know. But does anyone remember this tool from around 2010, 11? It was a social, few of y'all, yes. Do you remember what it was called? Yes? You can shout it out. Anyone? Yeah. So, for the young people in the audience, this was called Google+. And this was Google's attempt at creating a social network. Now, we don't use this anymore, of course. And the idea was, unlike Facebook or Orkut or MySpace back in the day where everyone could see everything, here, you could share things with certain circles. So I can have a group for university friends, or I can have a group for family and share things with certain groups. As a social network, it didn't do very well, but the story goes that they changed how their authorization worked internally at Google to build this. In fact, who here uses Gmail or Google Docs? Everyone? Yeah, of course. You know, if you've ever used, or if you've ever sent a Google Docs link in Gmail, you'll see this pop-up appear saying, someone needs access to this thing, can you give them access? And if you think about this, this is actually magic, because Gmail and Google Docs are two separate apps. But yet, there is a permission check that's happening in between. So how this works is exactly what I'm here to explain to you about. I'm going to give you a bit of a history lesson here on a primer on authorization. In the industry right now, when we say the word auth, people can conflate it to authorization and authentication, which are two very different things. Authentication is identity, who you are. So if you've ever logged in with LDAP or Okta, that is authentication. Authorization is what comes after that. It's permissions. So once we know your identity, what can you access? What do you have permissions for? And in the past, to do this, we have used things like access control lists. Imagine a long list of all the people who can read a document. Now you have another list for all the people who can edit that document. It's not very scalable. How many lists can you maintain? So after that, we had something called role-based access control, or RBAC. Now, if you work in a company, you might be familiar with this. You have a role tied to, say, software engineer, and all software engineers can check in code. You have a role that says sales, and all salespeople can access financial reports. But what if someone from sales wants to check in code? So you have to create a new role. Doesn't happen very often, but it could. And again, with role-based access control, it's not very scalable at complex use cases. So the industry came up with this thing called attribute-based access control. Here, everything is an attribute, where you have a bunch of characteristics. So if I'm trying to log into a system, it checks my IP address, my location, my email ID, maybe even my role. And based on all of this, it says yes or no. Now, both these systems work. They work well. But when you want fine-grained access control, it starts getting a little difficult. And Google, being at Google scale with billions of users and hundreds of billions of objects, needed something different. So they popularized this thing called relationship-based access control in their internal authorization. And we know exactly how their authorization works because they wrote all of it in a white paper that you and I can read. In fact, I recommend you read it. It's about 14 pages, very interesting, where they talk about how they built this authorization system. I've read this paper many times, and I'm just going to talk to you through this white paper. In this paper, which was released in 2019, so not many years ago, they say that they can do 10 million client queries per second, which is an insane number, and I'm sure that number has increased by now. If you're a developer like me, it's just an API, and I'll show you a demo of how that looks. And like I said, it popularized this thing called RBAC, or relationship-based access control. How does that look? The idea is there is a relationship between different things in your system. So instead of force-fitting a role or an attribute to something, you describe the relationship between things. So for example, say you have a, Say you have a document called Steal the Moon. That's here. And there is a folder, and there is a relationship between the document and the folder. Similarly, there's a user here. And the user can view the folder, so there's a relationship between the user and the folder, and hence, there's a relationship between the user and the document. So what can there be relationships in between? Well, one has to be a user. So if you have a Google account, you have something called a Gaia ID, which is a 12-digit ID. And in their system, you will have relationships to things like documents, Excel sheets, photos, YouTube videos, maps, any object. And the relation could be anything. It could be a member of a group. It could be an editor of a document or an uploader of a video. And the cool thing is, say tomorrow Google, they launch a new product, it's about creating a new object type and a new type of relation. So you have a user, you have an object, you have a relation between the two. How do you tell a system that this relationship exists? The paper describes this thing called a relation tuple, which is a format to describe a relation to a system. So how you read this is start at the hashtag and start at what's at the right. So in this case, user number 3 is the owner of document 123. And this format is very flexible because objects can also relate to other objects' relations. For example, in this case, the group security is a member of the group engineering. Think of a time a reorganization has happened at your workplace. It happens often. If a reorganization happens, you have to change permissions, email servers, who owns what. It's a cumbersome process. But in a case like this, it's about just writing a new relation. You would say something like group security is now a member of group DevOps. And that's it. Everything falls into place. What are we doing here? We have these relations. What are we doing with this data? The idea is to build a graph where your objects and your users and your relations are different nodes in the graph. And this is a directed acyclic graph, which means that the direction of things matters. I'm going to take the example of Google Docs. So in this case, you have some document, and you have a reader, Fred and Kim, they're readers of the document. You have a writer named Jill. The key thing in this graph is this little dotted arrow here in between, which indicates that all the people who can write to the document can also read the document. And this gives a lot of flexibility for a company like Google, because say there's a new requirement saying add an organization to this doc. Add the ability to add an organization. It's just a new node on the graph. So this node would be organization, where it's called Acme. You have an admin of the org. And you can say that all admins are writers, and we know all writers are readers. So you're drawing this graph. Now, when you try and access any Google Doc and say you're logged in, what is actually happening behind the scenes? How is that permission checked? Let's say the example is, can Jill read some document? The idea is, if there is a unidirectional way to go from some document to Jill via the reader relationship, that means Jill has permissions. So in this case, yes, we can go. So you can start at my document, you can go to reader, writer, and Jill. So there is a unidirectional way of going through from the document to the user. So yes, the permission is there. Let's take the example of Fred. Maybe Fred wants to edit this. Of course, there is a graph for a permission check. It's open source again, and it's not a general purpose database. So if you're thinking I can use it as an RDBMS like Postgres, it's not that. It's meant only for authorization queries, and it was written in Go. And fundamentally, you can do three things with this. Right? So you can say something like, can a subject take an action on a Sohan, view this document? Or can this person edit this code repository? It doesn't have to be documents. It could be any use case. You can also list all subjects that can take an action on a resource. So give me all the people who can view this document. And you can also do a reverse lookup. So say, give all the documents that a person can view. I'm going to show you a quick demo of how that would look. So this is a playground environment where there is a SpiceDB binary running in the browser. So you start by describing your schema, which are the different users and objects. I'm keeping it simple. You have a user here, you have an object here, and you define the relation between the user and the object. A user can be a writer or a reader. For each of these relations, you can describe a permission. So writers can edit the document, but readers and writers can view the document. Now, typically, you will be doing this in code, but this is just a demo. And once you have a schema, you would write relations. So say I create a new document, and I'll call it new doc. And I need writer permissions on that, so I will say user Sohan. So there will be an API call to write this new relationship. And then you can actually test out if someone has permission to access a doc or not. So I'm using a CLI tool, but you can do this via code as well. I will say something like this, right? Z permission check. Does user Fred have access to first doc? We can see that Fred is a reader of this document, but cannot write to it. So it says false. Fred does not have edit permissions, but Fred will have view permissions, and that is true. So again, this is what would happen in the back end. And just to give you a visualization, this is what the graph would look like. So again, if you've ever used a Google service, in their back end is something that looks very similar to this. Now, the question that I actually get asked fairly often is, does this scale? We need this to scale at the level of Google. What are some of the techniques used to scale? I can bring it down to two things. One is everything is broken down into a sub-problem, and the system tries to use the cache as much as possible. Now, Going into the details of this is another talk itself, but I'll try and explain it at a high level. Going back to our example, can Jill, right here, read this document? If you look at it, this is a union of 3 problems. The first one is Jill's name here? No. So that's no. Is Jill's name here? The answer is yes. So that is a yes. And we have the third problem, which is here. How the Zanzibar system will work in the backend is the first check is made, and it's like no. And the second check is made, the answer is yes. The result is returned to the backend. The backend does not bother checking this third check because it's already got the answer. But interestingly, it knows the answer to this already because it has made this computation. So that is stored in the cache. Remember this because I'm going to come back to it shortly. A question I get asked is, okay, you're caching all of this, but what if there is stale data? What if a permission changes? Maybe I'm removed from a document. That is a great question, and that's described in the white paper as the new enemy problem. So at T1, basically, Kara here has removed Lex, who's an evil person, from this document. And then Kara has made and changed this document, added new secrets, which Lex cannot access because he's not supposed to access it anymore. But because it's used from the cache, he actually attempts to read this secret plan, and he gets access, and there's chaos. So how do you solve for something like this? The Zanzibar paper describes this as the new enemy problem, and they solve it with something they call a Zuki, which we think stands for Zanzibar cookies. It doesn't mention. But anytime there is a change that's made, an opaque timestamp is attached to the call. So every time a document is changed or created or deleted, any new relationship, there is a timestamp that's created, which is attached to the backend. So if I say I want data that is fresh as of now, the system will bypass the cache and get me the latest data. If I say, no, I want an answer that is fast, but I don't care about correctness, it will get me something from the cache. And this is how it also gives Google flexibility. Because in a system like Google, there are what is called hotspots, where many people are accessing a document. And in the paper, they mention, we found the handling of hotspots to be the most critical frontier for low latency. So how do they handle that? There are 4 techniques, right? And I'm going to be a little technical here. The first one is a distributed cache. If you're in the cloud-native space, you might know how Kubernetes works. So imagine something similar where you have different nodes, each of which has a Zanzibar system running, and each of them have a distributed cache. So they each know which ones have solved which problems. So when a problem comes in, they're like, okay, that node has solved this already. We will route it there. And they get an answer back fast. And this is done through a system called consistent hashing. The second one, I said before that a timestamp or a Zuki is created every time a change is made, but they very smartly round up the timestamp. There is a window at which timestamps are created so that the backend is not overflowing with different timestamps. 3, all remote procedural calls, or RPCs, are internally optimized, both when a call is being made and when a call is being answered. There is cache at both ends. So you have much lower latency. And Google has an internal tool called Slicer, which they use for load distribution. And lastly, there is something called a lock table. Now imagine 50 people try and access a permission at once. Instead of all 50 traversing a graph, they create a lock table where only one can access it. The result is cached, and the other 49 use it from the cache. Now this might take a little more memory and bandwidth, but it's faster for the other 49 people. And what about the really hotspots? Say a video goes viral. or a document is shared with an entire organization. Remember when I told you that the subchecks are cancelled when an answer is received? Google detects that when it's a really hot spot, they actually go through the full read. So they would rather read all of the different subproblems and cache it so that people can access it faster because they know that this is a hotspot. And sure, this again uses a little more memory and bandwidth, but the subsequent checks for all the other people accessing it is much faster. And from the white paper itself, this saves the Google backend about 500,000 internal RPCs, and that is a huge number. Right? So all of these different techniques help it scale to the level of Google. And we've seen in the last few years that if you want to build permissions or authorization and you need low latency, because authorization is on the critical path, you have a high throughput of authorization checks, you need global levels of consistency, and you need all these different permission models, then a system like Zanzibar really shines. In fact, how many people here use ChatGPT? Yeah, everyone, yes, of course. If you have noticed, ChatGPT has a new feature called ChatGPT connectors. Right? So if you click on that little plus button, you can connect your Google Drive, OneDrive, SharePoint, Dropbox, Box, etc., and it would read from those documents, and you can query this. And this is big in the enterprise. And OpenAI actually uses SpiceDB. So this is a complex problem because you need to know the authorization system of Google Drive and match the user with the authorization system of Google Drive. You need to do that with OneDrive, SharePoint, Dropbox, and so on. And maintaining code for each of this is painful. But if you have any centralized authorization that can model different authorization models, well, then that's good for you. And OpenAI actually uses SpiceDB to process 37 billion plus documents. So that is a fairly large number. So Zanzibar really works at that kind of scale. So why am I telling you all of this? You know, what is the relevance of all of this? If you work in the industry, you might have heard of this foundation called OWASP, or Open Worldwide Application Security Project. Now, this is a foundation that looks at risks to web apps and LLMs, and they release this top 10 list every 3 or 4 years, where they tell you that these are the big risks in security to web apps. And the last list was released a few years ago, and the number one on that list is broken access control. Just open up any tech news and just type data breach, and you will see so many articles of millions of documents or pieces of data that has been breached because access control is complicated. Permissions are hard as our systems get more and more complicated. And a way to sort of fix that is to not write your own permissions and authorization, but think about using, you know, a third party or an industry standard. So a system like Zanzibar might actually be useful for you. Well, for next steps, I would say just read the Zanzibar paper. It's a very interesting read and written in English, not very academic. If you're into coding, you know, try out SpiceDB. It's completely open source. You can feel free to contribute as well. And yeah, I have a few videos up on the YouTube if you're interested. If you want today's presentation, feel free to click on that QR code, and you'll get it emailed to you. I also have few copies of the Zanzibar paper to hand out, so find me after the talk somewhere out there, and I have few copies of the Zanzibar paper you can read on the way back home. I hope you learned something new today, and enjoy the rest of the conference. Thanks for having me.
Thank you, Sohan. Any questions? Let's see your hands raised if you have a question. Or you can also meet Sohan in the next break in the speaker's corner. No questions? So let's send him off the stage with a big round of applause. Sohan Maheshwar!
Oh.